So here we have 1 pound of water. We have a heating element at some unknown thermal wattage sourcing from an AC electric stove rated at 220 volts RMS voltage parallel, and we have yet to calculate the electrical wattage at the element and the RMS AC current in amps. So this is an exercise in understanding the conservation of energy, as we cannot create or destroy energy. We can only change it in form or transfer it. So we will try to solve for the AC electrical true power in watts, as well as the AC current based on an 80% thermal transfer efficiency. So we'll place our pot, and I have pretty direct transfer of heat, and then we'll pour our 1 pound of water and start the stopwatch and see how long it takes to heat up. So we have 10 seconds in, so the stopwatch here. 20 seconds. 30 seconds. 40 seconds. Alright, we're at 40 seconds now. 50 seconds. 60 seconds, 1 minute. 70 seconds. 80 seconds. So 90 seconds. So 100 seconds. So right about 105 seconds, so boil. So anything higher than 212 degrees Fahrenheit will be super saturated steam enthalpy, so we're above 212. So we'll say 105 seconds to heat up 1 pound of water from an initial temperature of 50 degrees Fahrenheit to a final temperature of 212. So 105. Okay, so now based on this observation, we will be able to calculate the AC electrical true power and the amperage, as well as the thermal wattage based on 80% thermal transfer efficiency. And so we'll go to the calculations now.
So here we can access first the steam table so that we don't have to just rely on a linear BTU calculation, our delta T from boiling point 212 Fahrenheit minus the initial temperature 50 degrees Fahrenheit. So if we use a linear calculation, we're multiplying the delta T times the amount of water in terms of its mass. So 1 pound times the 162 degree temperized to boil. So that 1 pound of water theoretically it will require 162 BTUs of heat. So 1 BTU is the amount of heat required to raise 1 pound of water by 1 degree Fahrenheit. So the metric equivalent is 252 calories to 1 BTU, because a calorie is the amount of heat to raise 1 gram of water by 1 degree Celsius. But if we use the US system of measure, we use the British thermal unit, which is BTU, and that's the amount of heat required to raise 1 pound of water by 1 degree Fahrenheit. So then if we go to the steam table to get the most accurate non-ideal gas thermodynamic Rankine/enthalpy nonlinear distribution of thermal loads, we actually have 180.07 BTU. So we'll use this instead. So this is where a lot of calculations are actually in error. They're not using the enthalpy steam table. So this is the Armstrong steam tables, which are highly reliable and a universal metric, unlike corporation, municipal, government, and organizational steam tables. So the Armstrong steam tables are very accurate to use, including the calculator. So we've established 180.07 BTUs of heat to raise 1 pound of water from any temperature above freezing to boiling point 212 degrees Fahrenheit. So that's certified, and then we measured 105 seconds. And remember, that's an approximate value, but we really didn't want to go into the roaring boil that's over 212. So if you actually get a thermometer, it starts to just boil at 212. So 105 seconds is the recorded time. We measured 1 pound of water going from any temperature above freezing point to boiling point temperature, which is 212 degrees Fahrenheit. So 105. So we divide 180.07 BTUs over 105 seconds. So we calculate 1.71 BTUs per second. But then we have to also include the 20% loss in thermal transfer. So 80% thermal transfer. And so we can multiply 1.71 BTUs per second times the reciprocal or the inverse of the efficiency, 1 divided into 0.8. So we calculate a value greater. So 2.14 BTUs per second is the actual heat at the heating element. So the glowing red hot heating element, it's approximately a little over 2 BTUs per second. So we know 1 BTU per second is 1056 watts of power. So if we multiply 1056 times 2.14, we calculate 2,260 watts of thermal power. So that's the heating element. And then we have a 96% electrical efficiency through the heating element circuitry, or the heating element device itself. So if we were to take 2,260 watts and then divide that into 0.96, or multiply it times 1 divided into 0.96, we would calculate 2354 watts of AC, 2354 watts of AC true power, electrical power, flowing to the heating element. So we know that AC parallel electrical circuits involved in electrical heating elements are AC resistor circuits rather than RLC circuits. So their phase angle is 0 degrees. So the power factor is 1.0. So we can take the AC true power equation, which is the effective or RMS voltage E RMS times the effective current RMS IRMS, then times the power factor. But because we have a power factor of 1.0, the equation then behaves like a DC circuit. It's just the voltage times the amperes. So we can then quickly solve for the current at the heating element, or a kind of amp load that AC electrical stove requires per heating element, or at least the heating element we had used. So that would be a 10.7 amp or approximately 11 amp heating element AC electricity, and that's at 220 VAC, so that's RMS voltage, effective voltage. And then we have 2354 watts of AC true power per large heating element. So we had 2 large, 2 small on the stove. So that means if we approximate 22, there's probably like 40 amp circuit. That's actually a 40 amp 220 volt circuit on that particular AC electric stove. So if we approximate 9 amps for the smalls and 11 amps for the larges, 22 plus 18 is about 40. So the behavior on how the thermal transfer went through the water when we reverse the conservation of energy sequence, we can make very accurate calculations about source energy as it transfers. So this is just a fundamental lecture. So if you're ever dealing with thermal transfer in any type of power system, you can also go by the BTU method, or the amount of heat required to raise 1 pound of water by 1 degree Fahrenheit. And this is then equivalent to 1056 watts or 778.5 foot-pounds per second. And then if you want to convert the 775 into Newton meters or joules, then you can just divide the you can just then take the foot-pounds and then multiply it times 1.36, so you get 1056 Newton meters or joules per second, and that is 1056 watts. 1 joule per second is a watt. So we should think about the U.S. English system as it was completed, or we should think about the metric system as the completion of the U.S. English system of measure. It's like the metric system finished the absolute certainty. So just by looking at 1 BTU per second of heat is equal to 1056 watts or 778.5 foot-pounds per second, we know that 1 foot-pound is equal to 1.36 Newton meters or joules. So if we take 778.5 and multiply it times 1.36, we get 1056 Newton meters or joules. And we know 1 joule per second is 1 watt. So then 1056 joules per second is also 1056 watts. So the completion of the U.S. English system is the metric system. And that actually was validated when the inverse of 1 light second yielded 3.28 feet. And so the closest the U.S. English system made it to the absolute distance is 3.00 feet or 1 yard. So all of this interconnects. It's not a tangent. It's actually connecting distance to area, then to volume, and then into three-dimensional calculations, and then rates of change over time. So this is just a lab example video about how you can measure the heat transfer through water and then calculate the source thermal power. And then in this case, it's from electricity. So you can go the other direction and figure out the electrical efficiency and then actually calculate the source input power. And then because it's a heating element, the power factor is 1, you can just divide that input AC electrical power into the voltage and then get the amp rating per, at least this case, the large heating element. So this is just an exercise in the conservation of energy. Energy cannot be created nor destroyed, but only changed in form. Thank you for watching this video and have a great day.